conferences, technology standards, and professional educational activities. IEEE is the trusted voice for engineering, computing, and technology information around the globe. IEEE Information Theory Society memberships enables an individuals to stay current and updated within a chosen technology and ensures one is in touch with the peers. IEEE ITS is a leading technical society that focus on the processing, transmission, storage, and use of information, as well as the foundation of the communication process. Now, I would like to request Dr. Sridhar Iyer, Associate Professor, KLE Dr. MS Sheshgiri, Belgavi, under KLE Technological University, to introduce our today's speaker, Dr. Walid Saad, Professor, Department of Electrical and Computer Engineering, Virginia Tech, USA.
Thank you,
Yes,
sir.
sir.
I hope I'm audible.
Yes, sir.
Okay. So it's absolutely my pleasure to welcome today's speaker, Professor Walid Saad, and I thank him for accepting our invitation. His brief profile: Walid Saad received his PhD degree from the University of Oslo in 2010. He's currently a professor at the Department of Electrical and Computer Engineering at Virginia Tech, where he leads the Network Science, Wireless, and Security News Laboratory. His research interests include wireless networks, that is 5G, 6G, and beyond, machine learning, game theory, security, unmanned aerial vehicles, and semantic communications. Uh, Dr. Saad is a fellow of the IEEE. He's also the recipient of the NSF Career Award in 2013, the AFOSR Summer Faculty Fellowship in 2014, and the Young Investigator Award from the Office of Naval Research in 2015. He was the co-author of 11 conference Best Paper Awards at various conferences, which include IEEE Globecom in 2018, IEEE ICC in 2020, and IEEE Globecom again in 2020. He is the recipient of the 2015 and 2020 Fred Ehrlich Prize from the IEEE Communication Society, of the 2017 IEEE ComSoc Best Young Professional in Academic Award, of the 2018 IEEE ComSoc Radio Communications Committee Early Achievement Award, and of the 2019 IEEE ComSoc Communication Theory Technical Committee. He was also a co-author of the 2019 IEEE Communications Society uh, Young Author Best Paper. He was an IEEE Distinguished Lecturer in 2019-2020. He currently serves as an editor for several major IEEE transactions, and he is the editor-in-chief of the IEEE transactions on machine learning in communications and networking. I welcome you, Professor Saad. We look forward to your session.
So much,
Thank you,
and I'm
Dr.
gonna share my
Thank-
screen now. Okay, so just checking. Can you see the slides? So it's my great pleasure today to talk to you about a little bit about the current and future view of machine learning when it comes to wireless systems. So I went for the short title of AI native wireless 6G systems, which will kind of discuss a lot of things, I think, and I hope you find it interesting. So I'm going to start with a brief introduction, a couple of slides, just in general, what is it that we're doing now, what is it that we should look forward to. And the talk is divided into three sections. The two first ones is I'm going to talk a little bit, and this is something I'm going to try to hit on more in this talk, which is the idea of generalizable ML. So I'm going to talk about one problem there, which is called generalizable deep RL. I'm going to show you what we did in that space and how that work kind of builds towards more, not only AI native, but more intelligent, let's say, AI systems. And the second part, which is more on the flip side of the coin. So many of us use machine learning to improve communication, but also machine learning is gonna become an important user of wireless systems. So I'm gonna talk about that, particularly when it comes to edge learning. And then in the third part, which is gonna be shorter than usual, so I'm not gonna go into a lot of details here. I'm gonna talk about semantic communications, which we started to talk about early on, and about digital twins and their relationship with continual learning. So AI, where are we? Where have we been? And where is it going for? So AI and machine learning, which are two kind of tightly connected tools, it started all the way back in the island of Crete in Greece, where there was an autonomous man called Talos, who was an artificially intelligent man who was defending the island against invaders. And at that time, AI was really more the kind of thing of fiction. And currently, we are using AI to do powerful computation. computation, right? So today, I think AI is very effective at running algorithms, processing massive volumes of data, doing all sorts of inference, even conversing with you, right? As we get into that, and we are at the cusp of going towards AI as a brain, meaning it can mimic a lot of what the human brain can do. And I think the philosophical question here is whether it can become a human brain. I would say no at this point. At least let's hope it can generalize as efficiently as our brains. But at least that is something that we can aspire towards, right? So making AI more effective at learning with less input information, less training, if you want. And that could be one way to call it a brain, right? So it learns from experience, not necessarily from massive amounts of data that is used to train the algorithm. So again, today's AI is mostly centralized, and it's mostly using known protocols, right? And it improves, especially in wireless. When I say known protocols, I mean it's part of known protocols in wireless systems. Tomorrow, when it becomes a native, meaning a actual portion of the wireless system, it has to be distributed, multi-agent, and embedded at the edge. So it's no longer controlling known protocols, it's actually the protocol itself. And currently, we still rely on big data sets. We're hoping that the AI native world will learn with smaller data sets. And currently, you have this debate on model-based RL or model-based AI, model-free AI, or a combination of the two. We're hoping that we will have something which is explainable later, right? So we can mathematically understand what is it and how to actually design the architecture. It's heavily training dependent today, and we want to make it nearly training free. Of course, training free is a big goal, which we probably never going to attain, but I mean, I have the nearly world there to account for that. Currently, AI learns specific tasks. So it can do well in, let's say, recognizing a dog in a picture. But that's it, right? What we want it to be is to actually learn a skill, not a task. So we want it to learn how to identify animals, so that if it sees a dog, it knows it's a dog. But if it sees, a cat, it can somewhat infer that that is an animal, which is similar, but it's actually a cat, right? So we want it to generalize better to unseen environments, learn skills, become reliable itself, and I'm gonna mention that later on, and continual, meaning just as the human brain or as human experience is, the more you learn, the better you are. In AI, sometimes the more you learn, you forget it more quickly later. So, and that's not something good. So in this talk, I'm not going to talk too much about explainable. So I will leave that to future talks. I'm going to talk about the distributed angle a little bit, about the ability to generalize and the ability to actually learn skills in some sense. We'll touch a little bit about training free. Now, of course, if you look at the past year of wireless talks, you'll see everyone says brain, reasoning, all these words. And at the moment, if you really dig deep into them, they're still words. They mean nothing literally, technically, right? They're very nice to present, but they're not technically rigorous yet. And I'm hoping in this talk, I'll give you a few kind of flavors on how that can become a technical thing, right? When we say it can reason, what does it really mean? When we say it can be brain-like, what are some of the features we can do? And as I will mention, I will look at it in two ways: learning to communicate, that's where I will start, and communicating to learn, that's what I will do in the second part of the talk. So we'll start with the first new concept. We called it experience deep RL. And the idea is simple. It comes from this. We know that deep reinforcement learning has been a popular tool in wireless for good reasons, right? Because it has a lot of applications, it's effective, and so on. However, when it comes to applications that require reliability, things are not so rosy for deep RL, and we're gonna see why and how to overcome that. So again, ultra-reliable low-latency communication, URLLC for short, will be a key component of 6G. It was a key component of 5G. But now we have to go more extreme into more the need for more reliability, if you wish. So URLC is not new, right? There has been a lot of work. What's limited there? So one, most of the prior works focus on the classical application, which is short packet, uplink, IoT sensors, or they can call them drones or whatever, but it's really uplink short packets, and you have a massive of them. You don't care about rate, you don't care about the packet size, you just need to transmit those. And I think in that field, there's not much more to do, because the community has done a tremendous job there, and that already works in 5G, and I think it's an interesting area, but a saturated one. However, what if we have different environment? It's not small packets. It's not uplink, right? Like in autonomous vehicles, for example. Also, most of the work assume known models, right? So we use MM1, use little theorem, and that's good because it allows you to compute and do optimization in a better way. But at the same time, latency is inherently hard to compute and hard to model. We don't really know if these assumptions, MM1, MG1, and so on, actually hold. So people have started to say, oh, well, this is where AI makes sense. We need to do model free. And people looked at deep reinforcement learning. However, deep reinforcement learning will help you overcome the model approximation issue. However, in of itself, it has its own issues because it's slow to converge and it's not designed for URLLC. So you can see here the contradiction. We're trying to solve a problem, which is doing URLLC communication without models, but then we use a tool which in itself is slow to converge, so it's not low latency anyways, and it's not reliable because it's not very effective when you have extreme events. By extreme events, let's say a deep fade, a surge in traffic. So the fundamental question which we'll try to answer today is, can we design a reliable AI, reliable like the brain in some sense, that can work well under extreme conditions to achieve URLC, or more broadly, just handle reliable communication? Okay, so more broadly can have reliable links. So you can see the application itself is going to be very simple, something I'm sure many of you have worked with before. It's really the way we solve the reliable RL aspect that's of interest, and that's really the nice technical contribution, if you will. So consider a downlink, a single cell wireless network, where we're sending URLC type control messages to autonomous vehicles. Those don't have to be short packets. It could be actually videos or VR images if you want. And it's an OFDMA system where we need to allocate resource blocks. The downlink rate is given by the Shannon capacity. So you have the rho ij, the resource allocation indicator for user I at the station j, or sorry, at resource block j. You have one base station. The bandwidth, the power allocated to user I over RBJ, the channel over RB, the resource block j, and the Gaussian noise. So reliability, if you go to 3GPP, it's the probability of the end-to-end packet delay being below a threshold, right? So you want to maintain a successful transmission within a certain time duration. This is how 3GPP kind of phrases it. So we can map this, I mean, loosely, without getting into the math in a moment. But loosely speaking, this kind of means that your rate, let me show the variables, your rate should be greater than some function alpha, phi, which we don't know. That is function of the arrival rate of packets. So this is the packet per second, the Poisson arrivals, if you want. It doesn't have to be Poisson, but it could be. The packet size, the gamma, which is the target reliability, and the Dmax, which is my target delay, if you want. So this relationship is unknown, right? We don't know what it is. We need to kind of learn it. If you make some assumptions on the delay, you can find some expressions here. But if you say, well, delay is hard to model, so let's keep it model free, then you cannot really model this in closed form. So you need a different way to do it. So our goal, and as I mentioned, the optimization problem is very classical. Our goal is to solve this problem. We're going to try to minimize with respect to power resource block allocation, the total power over resource blocks, k, number of users, and over a time horizon t, such that the probability of the delay exceeding the max is less than 1 minus gamma I star. Gamma I star is the reliability target. The rate should be greater than, as I mentioned, the arrival and packet size. This is just a rate constraint, which you don't find in uplink short packets, but here you can have it. And these are just feasibility constraints on on the power and rho. So we have a positive power and the sum of rho. I mean, we allocate one resource block per user. So if you have a model for the delay, you can look at other papers from our group and others, where you can model this constraint, and you can usually use, let's say, Lyapunov optimization, stochastic optimization, and solve the problem. But without a model, this constraint is unknown, right? So we have to learn it. So we have a rate guarantee, as I mentioned, and this is challenging because of this model-free assumption, right? So if it's not model-free, the challenge can be overcome with optimization technique, as I mentioned, Lyapunov or others. So to handle model-free, we first think of this probability of d greater than d max. What is it in practice, right? What is it for the network? I mean, this can be approximated by this ratio, mu prime I over mu I. I is the user, right? So user I. Mu prime I is the number of packets that exceed the delay, right? The packets in violation of the delay constraint. And mu I is the total number of packets. So empirically speaking, the network can learn that delay, right? He doesn't need to know, the network doesn't need to know where that delay comes from. He just measures the packet delay end to end. It doesn't really need to have specific models for it. So it can learn it. So how to learn it? It's very, very useful to do reinforcement learning, because we know reinforcement learning can solve optimization problems. We know it can have some online approach to actually learn a model. So there's no doubt that it is a useful tool here. But classical RL cannot handle large state spaces. Here we have a very large state space coming from the channel, from the packet arrivals, and so on. So deep RL makes sense, right? So we can use here because it's appropriate to handle the large state space, but it still has challenges, and we will discuss them in a moment. So this is our framework. So we use deep RL. Forget the inside of it. I'll get back to it in a moment. But you have a deep RL framework. The user, the base station runs it. It can actually observe the rewards from the users. It interacts with the system, gets the rate, the users, the reward, and then it does its action state reward, if you want. Now, one challenge is that existing deep RL are not good at having large action spaces. So they handle the large state space well, and that's thanks to DeepMind's and development and others. But they do not handle the large action space well, because in computer vision, the action space is typically 4 or 5 discrete set of 4 or 5, like up, down, left, right. So it's fine. You don't need to handle it. Here we had to handle it. So what we did is we used a very well-known algorithm called the proximal policy optimization to solve our optimization. So remember, our optimization is this one is with respect to power and a resource block allocation. So instead of solving it with respect to power and resource block allocation, we solve it with respect to the rate itself, right? So we find the desired rate using the PPO algorithm. Then we feed that into something we proposed called action space reducer. It's really an optimization formulation. I'm not going to go through it here because that's not the core of my talk. It's an optimization reformulation of our problem. And we show that this reduces the action space significantly. It makes DeepRL more tractable. And this is why I have it inside this DeepRL framework here. So this division is our proposed approach. The framework is a classical DeepQRL network. So the reward function now, we make it function of a weighted term of the reliability and a weighted term of the power. And then we actually control the weights in a way to make sure they keep changing as needed by the reliability gamma I star, the target reliability of the user. And then we can prove that after convergence, so we're not guaranteeing convergence because, as you know, for DeepRL, that's hard to prove. But after convergence, we are sure that each user satisfies their reliability requirement. So gamma I t is greater than or equal to gamma I. I mean, this should be gamma I star for all I belonging to n. So we can guarantee reliability after you converge. Of course, keep in mind, this proof assumes the problem is feasible. If you don't have a feasible solution, then of course you cannot guarantee anything. So the action space, as I mentioned, one slide on this action space reducer. So the action space is too large. Non-wireless prior work, they don't care because their action spaces are small anyways. Wireless prior works usually ignore that. I mean, they say, okay, we cannot do much with it. We can just keep it. So what we did is this two-step solution. We solved for the rate using PPO and use this reformulated optimization problem. But the crux of the problem is this. DeepRL, is it reliable? Because I'm doing URLC here. I'm claiming to do reliable low latency communication. The answer is no, because first, it's slow to converge. Second, although DeepRL is good at handling unseen events, it's slow to actually handle them. So it's unreliable in some sense. There's a transition period where the DeepRL is fluctuating and your system is not meeting its target reliability, especially when there are extreme cases. And by extreme, I mean, as I mentioned before, a deep fade, a high traffic surge, something that the RL algorithm hasn't seen before. So how do we solve it, right? And this is where we went to back to this human analogy, which again, I know it's nice to illustrate, but it's not always very precise. So the idea was that, well, how do you actually make DeepRL better? In general, the way you do it is you train it offline, right, with some data. But in wireless, we don't have enough data, right? I mean, even if you do, I'm talking URLC here. I have extreme cases. most likely those extreme cases do not appear in the data you have. So then we thought, well, another big field in machine learning today is generative networks, the ability to generate fake points, fake data points. So the question for us was, is there a way to combine generative networks with deep RL to create experience just like humans have experienced, right? You experience something and then you know how to deal with it later, right? So you gain by experiencing more and more, and that makes you more resilient, if you wish, or reliable to extreme events. So can a deep RL brain, which is the neural network behind it, right, have this kind of experience? Of course, as I mentioned, you can argue we can do it with offline training, but you don't have enough data. So we need to improve that part of the problem. So what is GAN, which is one generative model? GANs are called generative adversarial networks. I'm sure you know them. So they're composed of two neural networks. One is called a generator, another is a discriminator. The generator tries to generate examples from some data set in order to actually trick the discriminator into thinking these are real data sets. And the simple example is this very famous celebrity photo, generating fake celebrity photos, right? So, and you've seen that a lot. It's called adversarial because this is a zero-sum game, and Ian Goodfellow proved there is a Nash equilibrium for that game. So how do we use it? We create a virtual environment offline where we have this GAN generating data. But going back to my point on the limited availability of real data, in wireless, it's very hard to get real data. I mean, in the US, we have a lot of privacy issues, and you need to know the operators, and even if you do, they don't give you much, and it's very difficult to use it. So on the one hand, I have limited real data, which I can find online or I can acquire somehow. On the other hand, we have models that can allow you to generate synthetic data, right? Like you can generate Poisson packets and things like that. So the question for us was, can we use GAN to basically merge real data and synthetic data, generate data points that are compliant with the real data, that increase my experience and can actually generate some of the extreme environments, right? They generate more data, which is compliant with the real data, which is controllable through synthetic data, but it's also not, it's also generative. It's not real, it's not conditioned on an operator giving you the data. So this is how we create a virtual environment, and I'll show you in the next set. Of course, once you train offline, you deploy in the field and you kind of run the department. So we went back to the GAN literature. Turns out that in 2015, Apple was looking at a similar but different problem also. So they were looking at this problem. They had unlabeled real images of eyes looking in different directions and from different, I think, genders, right? Females, males, and so on. And they wanted to actually create, and they had a very strong simulator that can create synthetic eyes. What they wanted to do is to create refined synthetic eyes that complies with the real data, so that they can actually expand the data set of unlabeled real images. And they developed something called the GAN-based refiner. It's called refiner GAN or GAN-based refiner. What we do is they did not do RL with it, they just generated these images. What we did is actually we borrowed this concept and we did the same in wireless. So we have unlabeled real information. For this paper, we looked at packet arrivals and channel. We have synthetically generated data sets based on models, like channel models, arrival rates. And we fed them to a refiner, and we had a refined channel and packet arrival data. Then we used that to train the deep RL. Okay, so it's a very intuitive idea, and this gives you experience because now I can control how much and the type of data I'm being generated here, and it's really great for creating a bigger data set. So let me show you some simulations. We use a real data set from online, I think Crawdad or another known database, which had packet sizes and inter-arrival times. So I'm comparing four types of deep RL agents. One is our proposed in red. One is the classical deep RL, vanilla deep RL in dashed black. One is deep RL trained with real data. One is deep RL trained only with synthetic data. You can see that they all, first observation, they all converge almost to the same point. Okay, so in terms of the final reward, average episode return is the same for all. But the difference is really here. Notice the comparison between the red curve, ours, and the vanilla deep RL. Vanilla deep RL has no experience. He needs about 50 episodes to converge. Ours converge almost instantly. And you can see the synthetically pre-trained also needs about 40 episodes to converge. And the pre-trained with real data is the closest to ours, but we're a little bit faster as well. Now, what about these extreme events? So what we did next is at epoch 100, we inserted an artificially inserted surge in traffic. So we kind of increased the traffic, the packet sizes and their inter-arrival time. What happens? You can see that vanilla DeepRL needs about 100 epochs to actually adapt to that. Which, if you're doing, let's say, video streaming, it's quite fine, no problem, right? It's fine. You can wait a little bit. It's not a problem. But if you're doing URLC, this transitory period is a disaster, because you're saying I'm solving a URLC problem, and then you insert a DeepRL agent which is not reliable. It needs 100 epochs to actually converge. So that's really contradicting with URLC itself. In contrast, you can see ours immediately, almost immediately converge, almost immediately. And it's much better also than the synthetically pre-trained and the real pre-trained. So you can see this idea of experience allows you to actually cut significantly your time to converge, to adapt, and it makes DeepRL reliable, right? And that's really the main message of this first part of my talk. So open questions. You can actually explore other things. You can explore something called these entangled representations, which means I get a piece from one data, a nose from some picture, an ear from another picture, and I create a new picture. Can we do something similar in wireless? I haven't done that, but that's something to think about. You can also extend to multi-agents, right? So some of our works, I will talk a little bit about the continual learning aspect later, but can you have a multi-agent generalizable RL? Yes, you can see my work with my former student, Yehu, where she looked at the use of meta reinforcement learning. Can we have a multi-agent GAN? You can also see my work with also my former student, Aiden, where he looked at distributing the GAN itself. So I own a piece of the data, you own a piece of the data. Can we come together to generate a full piece of the data? Also, what about RL is always looking at, even in my results here, I say average expected return. What if I want to look at distributions, not averages, which is important for URLC? You can also see my work with Chin Zhang, my former student, and you can see what we did there in that respect. And also here we use the DeepQ network. You can design a much better architecture. We've done a lot of work with Dr. Mingzhi Chen, also my former student, who's now at Ericsson actually. So the next second part of the talk, I'm going to talk more about the flip side of the coin. So here we used RL or AI to improve wireless. What if AI is a user of wireless, and why is that important? This is a work we've done in 2020 actually. It was published in 2021, and this came at a very right time where you started hearing more about this idea of joint learning and communication. And what does it mean? I'm going to tell you today. So we were the first to propose it in this particular paper, and it actually picked up quite a bit, because at that time there were a convergence of two paradigms. One is, in the machine learning literature, people were looking at federated learning. And it was proposed in 2017 by Google. We started working on it in 2018, and this was kind of one of our first work there. In the wireless community, they were trying to think, okay, what if we use federated learning to improve wireless, like I did with RL? But then you had these autonomy systems, right, that might use distributed learning and wireless together. How do we merge these two? So what is FL first? What is federated learning before we get into the problem itself? So if you have any machine learning model, it can be trained in a centralized way, where you have a cost function f, function of some neural network, weights w, input data set xik, output data set yik, and their ki samples and new users. You can send all the data to a cloud. That cloud can optimize this, minimize this function, typically using a sort of a gradient descent algorithm, and then it can find the optimal training. Now, Google in 2017 came and said, well, most of the time users do not want to share their data because the data is private. Can we do distributed training? Meaning, instead of sharing data, every user will have their own local federated learning model. They will share actually only the weights of the neural network. They don't share the data set. And then they call it a parameter server. I call it a base station. I'll tell you later why. Will actually create a global model G, which actually aggregates the neural network models we got and sends back that global model. And this iterative process was shown initially by Google in 2017 to actually lead to effective training. So you're training your database, or your data set at the base station. You're not sharing data. You're only sharing neural network weights. And since then, federated learning explodes as an important distributed learning algorithm. Now, what we said at the beginning is, well, if you look at the federated learning community, what are they doing? So a lot of the work is focused on privacy, and for good reasons, right? Because at the end, perhaps the most important motivation for federated learning was to ensure privacy. But, and some of them were saying, well, maybe those weights are very large, so we need to make them smaller to send them over a bandwidth limited channel. So there has been something called communication efficient FL. But in those works, they usually do some sort of compression or quantization of these weights and send them over the channel. We came and said, well, look, if you're saying federated learning is gonna be deployed over massive systems, like autonomous vehicles, like hundreds of sensors, like many devices at home, these devices have to send their data sets to a base station. And the best way to do it is to send it over a cellular system, right? 5G at the time, or 6G now. So you want to do that. That means that now you have a fundamentally different problem. Now we have an AI model called federated learning, who is actually using the wireless system as a means to transmit its information. So now the wireless system is not serving a video streaming. It's not serving your traditional control parameters. It's actually servicing a new service called distributed AI. So the question we ask is, what is the impact of wireless, meaning not just bandwidth, as the federated learning community has done, meaning packet errors, fading, interference, all these aspects of wireless cellular systems on the accuracy of federated learning, right? So, and this, see, I mean, going back to the native aspect, you can see here, FL is a native user of the wireless system in some sense, right? So AI is not doing anything to communication. They're probably navigating a car or doing some other task, but they're using the wireless system, and the way they use it affects how good they are in their inference. So the FL training process in a wireless network now becomes this way. The global model and the local models will be shared over wireless links, so there will be transmission errors, and there will be delay and energy consumption. So the question is, how do we use communication to support federated learning? And this was at the time the first question that asked this directly and in a very concrete manner. So again, this is the same slide as before. I'm gonna skip it. So the system model we have now, we have a cellular system with one base station, users, and these users are doing federated learning. We are using the uplink of the cellular system to transmit their local weights. They're using the downlink to transmit the global weights. The uplink transmission rate is given by this. It's function of R, which is the resource blocks used, power, of course, resource blocks again here, and you have power, channel, interference from other base stations, and you have the noise here. Same to the downlink, right? So you have bandwidth and so on. Now, the first equation on the bottom starts to show you how ML or AI and wireless come together. So here I'm saying the delay of transmitting uplink is actually the size of the weights. These weights are machine learning weights divided by my capacity, and the downlink is the size of the global weight divided by capacity. So this slide shows in a simple way first how machine learning and wireless are now tied together. So you can no longer separate them in this particular application. So now transmission errors, right? When you transmit these weights back to the picture I had everywhere, this one, there is a transmission error. So they arrive to the base station in error, especially in uplink. I'm gonna ignore the downlink in this paper. So we assume downlink is effective, and because we don't do a lot of downlink transmissions, we're not gonna focus too much on it. So what we're gonna say is there's a packet error rate given by QIN for user I over resource block N, and this is a classical equation from any communication theoretic book. You can find the packet error rate, which is function of the fading, interference, power, and so on. Now, what we're going to say is that the base station, if it receives a certain weight with a high error, it will discard that weight when doing the global averaging for federated learning. So you can see this equation is important. It shows you directly now the global model, which is a federated learning weight, is function of which users are associated to the base station A, the power of the users, and R, the resource block allocation. So machine learning depends on wireless. And you have this function C, I'm going to explain it here. C just is an indicator. It says that if the user I needs to be discarded because of high packet error rate, this will be 0. If the user I it has a good packet error rate, then it will be used. So it's kind of basically uses QI to decide which weights are used, which weights are not. KI, I mentioned it before, is just the number of samples for user I. So the problem formulation now, the training of federated learning is now a minimization, not only function of the weights, which should be there, but I don't have them because we assume them to be done separately in some sense. It's a function of the wireless network, right? So I'm minimizing with this, I'm minimizing the accuracy or maximizing the accuracy, minimizing the cost of federated learning, which is now function of the wireless network, right? Not just of the weight, it's function of the wireless network and function of the data set, of course. And it's now in the constraints, you have an energy constraint E, you have a delay constraint L plus L less than gamma T. So you can see in this slide, this is where we came up with this concept of joint communication and learning, because now you're designing the two together. I'm improving the training of federated learning, but to do that, I'm controlling the wireless network. And I think that term has become more widespread now, but this was the first paper that said we should look at something called joint communication and learning, particularly for federated learning. So you can see, I mean, I mentioned those, the constraint, the power allocation matrix, and so on. Now, to solve this problem, we need to first understand what is the impact of these packet errors here, which are here, on the convergence of federated learning. So this is the main theoretical result of the paper. We prove that there's an upper bound on the convergence point, which is function of all these metrics, right? Let me look first at this term, the last term. So GT plus 1 is the global model at time t. F is a function of the gradient, because at the end, federated learning is gradient descent. G star is the optimal solution. And forget this term for a while. Let's look at this one. A is a number between 0 and 1. It's function of many parameters, including the resource block, the packet errors, and so on. And this is the convergence point. So you can see if A is less than 1, T goes to infinity, this term is 0, right? Which means federated learning converges. However, because of wireless, you have this first term, which has QI, has AI, has also A, and has these all factors that depend on the network. And K depends on the data set as well, but the network is the important part. Because of this term, you might not converge to your optimal solution. So wireless errors affect accuracy, right? And that is something that was not known before, right? So wireless errors affect accuracy. So this is a key characterization of FL, right? So convergence is affected by packet error rate, user association, and the wireless network. This result is for full gradient descent. The paper has it for stochastic gradient descent. It's similar, actually, not too hard to extend. And with this in mind, we show later that with this proof, solving this problem ends up being minimizing this term only. And luckily, the optimization problem itself is easy. So we can solve it. We can find the optimal power allocation, which is the minimum between Pmax, Pi, gamma E, which is a solution to this equation. And you can find the uplink resource block allocation using the Hungarian method. So the solution of the optimization problem is easy. It's really the proof of the theorem that was the main contribution. So again, now it's a new view of learning. And before, we used to use learning as a optimizer or enhancer of wireless protocols. Here, think of AI as a user of wireless. And this is a precursor to semantic communication, and I'll tell you in a moment why. This was kind of the idea initially, but it also relates to that. So some simulation results, I'm comparing with three baseline C is a very basic algorithm.
Please mute yourself.
So baseline C is a very basic algorithm. It's a really randomized, not interesting to compare. I mean, we're much better anyways. Baseline B is Google's algorithm, which is unrelated to wireless. They say wireless is a black box and we transmit over it. Baseline A is our algorithm without resource allocation. And you can see that we have significant gains across both in terms of identification accuracy. We have also, this is as the number of user changes. This is as the number of resource blocks changes. Okay, so you can see we have a significant gains over the baseline B, which is really the important baseline at the time of this paper. Now there are others, of course, but at the time of this paper, baseline B was the only available baseline from others. So what is interesting in this area, you can see a lot of work. So we have recently an ICC paper, which got the best paper award at ICC recently, which looked at the green aspect of FL. How do you enhance energy efficiency with quantized neural networks? We looked at convergence analysis, which was the ICC best paper a couple of years ago, where we optimized convergence time. And we looked at fully distributed FL without a base station. We looked at some game theory aspect, more economic side. We looked at FL to optimize wireless, right? That's the traditional view. And we look at it as also with drones. Actually, this paper says submitted here, but it was accepted a couple of weeks ago on autonomous vehicles on the road. Now I'm gonna conclude with, as I mentioned, there's two topics where I'm gonna be a little bit shorter than what I did before. So this interesting topic is on semantic communications. We had some discussion early on. So we're recently advocating for something called Neurosymbolic AI, which will make a lot of sense for semantic communication. It really brings in reasoning. And this is a work with my postdoc, Christo Thomas, who is actually from India as well. We've been looking at this recently. This paper was submitted to a conference for publication. So intent-based network is this new idea that says it's similar to goal-oriented, if you want, where we want to design a system that can be given a target, like improve network quality, and it can do it by itself. So it can find a way, figure out a way to do that goal, right? I mean, be energy efficient, and then we let it run. It can define that behavior. It can meet the behavior we set for it. It can meet the goal we set for it. And this has been in a discussion for a while now. So and this brought up the idea of semantic communication, which is the idea of sending, instead of sending bits, I send the meaning of information. Now, of course, the word meaning or semantic, which are actually synonyms, means a lot of things, and it's a little bit vague to define. So for us, what does it mean? For me, meaning or semantic is really a representation of the information. Just like we represent English, right? You have a syntax, you have a certain structure of your, let's say, vocabulary. Then semantic is really something similar. It's the meaning of the data, right? How can I represent that meaning? And then transmit that meaning towards the device, to the receiver, and the receiver will be able to extract the information from the meaning. Now, there is one example given there. While I'm not a big fan of it, but I think it's good to illustrate. It tells you that in semantic communication, instead of sending the actual data, what I actually send is an explanation of the data. So I tell the receiver, I'm seeing a dog, instead of sending the picture of the dog. And I expect the receiver to recover it. So I'm sending English words, if you want, and I'm expecting the receiver to recover it. That's a really good example, and it kind of explains semantic. But my word of caution is the language itself for semantic communication is really not English. We need to invent that. What is it? I don't know. We're trying to look at it here. I mean, it could have some English basis, but it needs some sort of information theory / logic basis. And that's really what I want to say. So the idea, though, is really like this. I explain to you something like a teacher and an apprentice. I explain to you something, and I'm hoping that in the future, you're able to actually understand that topic more and more on your own, right? So you can do more with the data. And really the keyword here is do less, do more with less, right? So I send less, you do more. What is less? It's a representation, a semantic representation of the information. Now, a lot of people call this beyond Shannon and things like that. While again, I think these are nice buzzwords. In reality, you're still governed by bits at the end. So semantics will be represented by bits somehow. So I'd rather avoid those when needed. But it's the idea of beyond Shannon came from an introduction by Weber, where he said, well, Shannon is looking only at the technical part. He called it level A. But then we have semantics, which is level B, and the effectiveness, which is level C. That's a nice qualitative way to explain this, but it should not tell you that we're actually circumventing what Shannon has done in some sense. So the prior works, there has been quite a bit of work. So there's some limitation. Many of them are qualitative, so they just explain what semantic is. Many of them ignore the reasoning behind the data generation, meaning where did the data come from? Because if you can explain where the data came from, the receiver can recover it. And they limit the discussion to some attributes, like, they say, there's some relationship between information and some attributes in that sense. They're not really generalizable. There's a couple of papers that looked at the idea of reasoning, but they kept it loose. They said reasoning, they did not explain what it is. And they think of semantic communication as a layer, as opposed to being a concept that actually crosses the layers in some sense. So we have some proposed approach. Again, this is ongoing, and it's working out. We're looking at neurosymbolic AI. Why? Because neurosymbolic AI is a new trend in AI that says the following. It says that in the 90s, AI was really called symbolic AI. It was this idea of really artificial intelligence, where you can learn a concept and generalize from it. And this was used to be called symbolic AI. It's some logic rules, if you want, out of which you can generalize information. The problem with symbolic AI and why it did not pick up at the time much, because it's very complex and it doesn't do well with massive volumes of data. And then came neural networks, right? Neural networks were the champions. They're amazing at processing data, they learn very well, and they have been the standard AI for many years now, right? But then people started to say, well, we should probably go back to the roots, because deep RL, or deep learning in general, does not generalize well. It does well with information you give it, with training, but it doesn't generalize well. Symbolic AI generalizes well, but it doesn't do well with massive volumes of data. So people are starting to think, can we combine the two and create something called neuro-symbolic AI? Some people call it neural symbolic AI. It's the same. So in this work, we actually thought that it's really good for semantic communication, because we need to learn, and at the same time, we need language, we need rules, we need ability to generalize. So you can see in this picture how we kind of view neurosymbolic coming into the picture. Everything green is symbolic AI. It's the creation of these language rules, updating the knowledge base, and doing this kind of reasoning. So we use some sort of information theory-based language here, proposed by Carnap, and this is kind of gives us the symbolic component. Now, the neural component, it comes from something called GFlow nets that was proposed by Joshua Bengio recently, which actually also combines some reasoning angles. So we can even think of GFlow net as neurosymbolic in itself. It allows you to actually learn the causality of the data, the reason why data was generated, and generalize from that. So we use it, as you can see here, we use it to transmit the state, extract the semantic state. And again, we have something called the grounded description, which think of it as a meaningful way to describe language. So now I describe a world state with language, and then that language is used to take an action at the receiver. Now, again, as I mentioned, I'm not going to go through the details here. I'm going to show you some simulation results. You can see that neurosymbolic AI does much better compared to systems that send everything. So this kind of motivates semantics. So we're sending less to do more. And we also show that it's much better than some of the logic algorithms that have been proposed recently in semantic communication system. We do much better in terms of semantic reliability and so on. Now, the last topic, again, a brief overview. This is actually accepted to SPOC. So here it was submitted. It's more about this continual learning in digital twins, and I'm going to conclude with this briefly. So what are digital twins? Digital twins are a virtual representation of a physical system, like this car going around this vehicle. And digital twins are something that you can use to actually control the system. So you can, do some simulations here, send back feedback to the real system, and kind of twin it. It's really a twin of that system. Now, the system itself, the physical system, may go through different episodes that have environments that are non-stationary. So moving from here to here, let's say the weather is great here, suddenly it starts to rain. And to capture that, the twin must update its information. Now, one way to do it is to always send everything, but that's really not effective, right? Because neither from a communication nor from a training perspective. And also to actually update your system here, there is a desynchronization time, which we call delta T, which means that your twin, there's a period of time where it does not match the real system. And these two aspects, which is not sending everything and reducing this desynchronization time, have been ignored in the literature. So our goal here was to create a new machine learning model that allows me to update the twin over non-stationary environments and minimize this delta T. So again, I'm gonna skip the math. I don't have a lot of time, but this is kind of the optimization problem. We're minimizing training the digital twin algorithm in a way to minimize the loss function, which is the machine learning model accuracy, and the delta T, which is this desynchronization time. Now, to do that, we observed that because the environment is non-stationary, using classical ML will require a lot of data. Then we thought there's this emerging trend called continual or lifelong learning, where the idea is that you don't forget what you learned before, which is a problem called catastrophic forgetting in deep learning. So how do you avoid it? You use continual learning. So in this work, we actually use continual learning for trends. So we use something called elastic weight consolidation to do regularization for the DT history in the loss function, and we repose the problem. So we repose the problem, in a way to optimize stability, meaning the neural network will converge to something that works, and plasticity, meaning the neural network can generalize. And we showed that this actually works. Again, this is just an early work, if you want. And we showed here, I mean, the simulation will give you some interesting things. On the one hand, we showed that the accuracy of continual learning is as good as something exhaustive. But exhaustive learning, you see on the right-hand side, has a lot of desynchronization time, right? You can see it's not effective. The twin will not be a twin for a long period of time. On the other hand, continual learning is as good as single task learning. Single task meaning the fastest you can do it. The problem with single task learning is not very accurate because it's not continual. And so what's next in AI? I think this idea of meta experience generalization is something you should think about a lot. How do we remove training? How do we do real reasoning? Generalize from small data through causal learning, where neurosymbolic AI plays a role. And there's something called curriculum learning as well, which is interesting. It's a rich field of application, and you can look at a lot of things. I will conclude now with a few of our research areas. So we've been doing quite a bit on 6G. There's quite a work we've been doing on terahertz and RISs. I'm happy to talk about that in a future presentation. Also on extended reality. I talked about semantics today. We've done quite a bit of work on control and communication for drones, using also joint sensing and communication. We've been doing quite a bit on distributed reasoning and learning, as I mentioned today already. We have a project on the age of information. We have some works on quantum AI and quantum networks recently. We are doing some works on air pollution monitoring using transformers. I've done quite a bit of game theory throughout the years, and we still do that. And there's a few other things we're working on with a smaller focus. And finally, again, AI native or AI reasoning and so on is an exciting area. Think of the two sides of the coins, using wireless to support learning, using learning to enhance wireless. And semantics is an interesting area. Be careful what you do there. Don't be kind of going with the buzzwords in some sense. And finally, I'll be happy to answer questions, to reach out for collaborations in the future. And thank you again for the invitation.
Thank you very much, Dr. Walid Saad, for spending your time for today's webinar. It was indeed a very informative session. I think there are one question is posted in chat box, sir. Hello.
Yes. Yes.
Yeah.
I'm trying to read that. Yes. So I can see the question from Dr. Padmashri. So in intent networks, if the nodes have to incorporate algorithms and decision-making capability, will it not hinder the performance, which can actually slow down the activity of data reception and transmission? That's a great question. I think yes and no. I think there will be a period of time to learn the language. And it depends how you define that language. But during that period, there is some loss of efficiency. But in my opinion, the way it should work, and as I mentioned in the introduction, we're going to have a paper that explains that. I think at the beginning, you actually send both. So you send the semantics so that the receiver learns, and you send the real data. Because at the beginning, you don't have a language. And you need to send the information. I mean, there's no way. You have to use Shannon. You have to use the regular transmission. But over time, if this symbolic AI and is well integrated, and these capabilities of generalization work well, then this overhead will no longer be important. And also keep in mind that this is not all applications. Right? There will be use cases where it will make sense. There will be use cases where it will be maybe a lot of overhead and you don't need to do it. And the use case where it makes sense is going back to my point on FL, is the case where your user is an AI algorithm, right? So if your user is an AI algorithm, then using this kind of semantic communication, it makes a lot of sense.
There's another question, and I will read it for you. It says, what computational platform was used for the simulation?
Yeah, so most of the simulations here, because they're analytical, were MATLAB. Some of them use Python, some of them more machine learning things.
Okay. There's another question which says, how was the exploitation and exploration handled in DRL, in the problems which you addressed?
Yeah, so because we did an offline training, it was easier to do exploration and exploitation. We used the known policy. I think we used, if I remember well, either Boltzmann Gibbs or Epsilon Greedy. We did not really do much to the policy there. We used a known one.
Okay. And there's another question. Sorry. Okay, I'll go ahead and read the question. It says, in SC, do we need extensive training of receiver to get the correct data expect?
I think I mentioned that earlier. I think you need a period of time where you will send both the, if you want, the logic and the regular data so that the receiver is tuned to the language. Once it knows the language, it doesn't need any training anymore, right? I mean, ideally, there could be use cases or examples where you might have to do training a little bit, but the extensive training is really at the beginning to learn the language.
Uh, I don't see any more questions there. I have a couple of questions myself.
Sure.
The first one is on the optimization equations which you shared. I think they were in a couple of slides. So I believe these optimizations would be NP hard to solve it. So how do you really go about solving them? Did you design any heuristics for them?
So yeah, let me go. So this one here, it's really a heuristic for the continual learning. It's a heuristic. For the deep for the, let me see the other one. This one actually, we can show that this can be just minimizing this.
Okay.
And minimizing this turns out to be easy, actually. I mean, there's some convexity and so on. So we solve, we decompose into two, we find the power, and then we use Hungarian method. So it turns out to be easy. And the first one, we use DeepRL because that's the only way we could use it. We could solve
Yeah,
it.
right. Okay. Yeah, and my second question is the same which I asked you before the session. It's on semantics. So there's been a lot of talk about semantic, and I think you addressed that when you were talking about it. Many people in the community are thinking about semantic communication as an advanced version of compression, where you are doing a lot of compression at the source and then the opposite at the receiver. So what's your take really on that?
Yes, it's not really compression because you'd expect the receiver to actually come up with information that he has not seen before. And that's not always done in compression. So compression is part of it, but it's not the full picture. Let's just put it this way. So the full picture is that you're intelligently controlling the information now. And that is related to the reasoning aspect. But I mean, at the end, yes, you're trying to do to transmit less, but it's not just compression.
So I don't know if you have a couple of more minutes because two more questions just
Sure,
appeared.
sure,
So, yeah,
sure.
okay. So the first one reads, how much is the power consumption of these learning algorithms in the wireless domain? Is it sustainable enough? Is the expected gain because of the usage of AI in wireless sufficient enough to offset the power required for AI processing?
Yes, that's a great question. I think I'm trying to find a slide where I mentioned it briefly that. So I think we need to study more energy. And this is why I mean, I would refer, we have a recent paper called Green AI or quantized federated learning. And it looked really at the energy aspect because I think, to be honest, I think the gains will be justified. I mean, AI will give us strong protocols in many cases, right? And it's not going to be the solution to everything, but it's going to have interesting integrations in terms of resource management, even at the physical layer. But we need to study more the energy aspect. I think people have been ignoring it, especially the computing. I think the transmission RF energy might be okay, but the computing energy is an issue. And in this work with my student Minsu, we're going to have a journal version soon. We looked at strategies to reduce the energy by kind of having these quantized neural networks. But at the same time, that actually makes your accuracy worse, right? So how do you trade between the two? I think this is an interesting area of research. You should work on it in some sense. And we're looking at it now. And I see another question on the GAN.
Yeah.
As the GANs are not proven to reach Nash equilibrium, was it good if not? So yes, so the way we used GAN here is we used the classical GAN, so we did not contribute to the architecture, and we're using it offline. So it was good enough for us to generate the data. It was not used to in an online wireless model, so it was fine.
Yeah, there are no more questions that I see. Okay. Amber sir, do you want to take over?
Yes, sir. So as we come to the end of the webinar, I would request Dr. Amber Basta from IIT Institute of Technology, Bangalore, and also our IEEE ITS Secretary, to propose the vote of thanks. Over to you, sir.
Yeah, thank you, Dr. Aliki and Dr. Iyer. Myself, Dr. Ambar Bajpai, as the Secretary of ITS Bangalore chapter, would like to came here for the vote of thanks. So thank you first of all to Dr. Saad. He's a big name in communication AI research. I know well. I read some of your papers. I am also in B5G and working on channel codes. And he basically briefed the three different sessions, and he talked about various machine learning models, talked about the GAN, RL, and he interestingly a federated learning. This is a new term to me and all of you. He also discussed also new challenges, what area he is working, what are the various research problems in this particular field of different modeling techniques, and lastly he touched on the semantic communication with neuro problems. So this is a very interesting and informative talk to all the audience here, which I think in national level we promoted. So I think entire Bangalore section and the other research scholars got benefited. It's very indeed a very interesting and very informative talk. Thank you once again to all the participants and our team, Dr. Ayer, Alagi, and Dr. Walid once again. Thank you very much for
Thank
joining
you.
us today in the morning. Thank you.
Thank
Thank you
you.
one
Thank
and
you.
all.
Thank you, Dr. Amber, for your vote of thanks. Also, I request all the participants to mention their name with proper initials and mail ID, which will be considered for attendance in the feedback. Thank you, one and all, for your patient listening the webinar. Have a great day. Thank
Thank
you.
you all. Thank you. Bye.
Thank you, Professor Saad, for accepting the invitation and for the wonderful session. I know you keep very busy, but thank you for all your responses. And if you don't mind, can we share your email ID for future collaborations if anyone wants to get in touch?
Sure.
Thank you.
Please do.
Thank you. And we'll definitely contact you again for another session. This has been brilliant. Thank you very much.
Thank you. Bye.
Yeah.
Thank you. See you. Bye bye. Thank you, Abba sir. See you.
Thank you. Thank you. So I hope everyone has downloaded the certificates. I'm closing this meeting for all.
Okay, sir. See you. Bye.
See you. Bye. Bye. Anyone left out for the certificate? This is the last time I'm asking.
Sir, my certificate still not come, sir.
Yeah. I have just shared. You please take the feedback.
It's come now, sir, for mail.
In the chat window, you can see the link, please.
I submitted, sir, but not came to the mail. Hello?
Okay. This email I have noted down. I will take care of this. However, I request this link is perfectly working and we have tested this. You please download your certificate.
Okay, thank you.
Hello, sir.
Yes, please. Yeah, please.
Sir, fans, the link you will be sending, sir, to download the certificate.
Yeah, it is in the chat window. Can you check the chat window?
Sir, my certificate not came.
Mention your email ID. However, we have tested this link. It is working.
I am
This is
testing
not a
my mail
problem.
ID,
Maybe
sir.
some problem from your side. Kindly check, please.
I will all done, sir, properly.
Okay, on that case,
I send it my mail also, sir.
Yeah. You share us the email. If you are not getting, we will look in this. Also, I will share this to all the participants, the today recorded session to all of you.
Okay, send me, sir, please.
Yeah.
Okay, thank you.
Thank you. So I'm closing this meeting. One and all. Thank you very much.
Okay.
Okay. Yes. Thank you and good night.